All right. Good morning, everybody. Hope you're ready for a fun training today. We're going to be talking about AC and DC coupling of a PV system, especially as it relates to PHI batteries. So just a little bit of housekeeping. There is a question and answer bar at the bottom or top of your screen, depending on your layout. Make sure to throw all your questions in there, and I can get to them either during the webinar or at the very end if I haven't answered them already. We'll do a Q&A section at the end. If you need NABCEP credits, just go ahead and email me. My email is going to be at the very end of the presentation. Try to email me right away and I'll get them over to you within 48 hours. And without further ado, I'm going to go ahead and get started. So as a general background and overview of our company, we were founded in 2010, in case you're not familiar with us. We actually were founded as OES Energy, and we've since changed our name to SimpliPhi Power. Now, since then, we've been used in all sorts of military, residential, and emergency response projects, generally just proving how safe that lithium batteries can actually be. You know, all lithium ion are not the same. When you compare lithium ion to lithium iron, the fact that there's no cobalt in lithium iron makes them a whole lot safer. And that has really set us apart from the market, as we've been doing that since 2010. And now everyone else is just kind of hopping on that train. So we have recently expanded our product line to include, a more diverse set of products, as well as ramping up our manufacturing capacity. One thing that's super relevant to today is UL listings. All of our products, where applicable, are UL listed. So that means they've been tested and approved as safe by a third party. Now, this is important not just for your safety, but also for building and fire codes as far as permitting, inspection purposes, insurance purposes, and if you're going to go to sell your house, you want to make sure everything is up to code. So to give an overview of today's topic, AC coupling and DC coupling. So AC coupling really is, PV panels are generating DC power. When you're AC coupling them, you're immediately converting that DC power to AC power. And before you can put it back into the batteries, you have to convert it again to DC power. So solar panels and batteries both run on DC. So when you're talking about DC coupling, that means your PV panels are producing DC power. It's coming right off the roof and into the batteries without converting to AC. Now, there is a charge controller in the middle there, tending to the batteries and making sure that the voltage and charge current is proper. So we're going to start with a summary and kind of deep dive into DC coupling, and then we'll get on to AC coupling. We'll do some examples of systems, some line diagrams, and yeah, lots of good stuff to come. DC coupling means you're generating DC power all the way from the PV panels, shoving it into the batteries, as well as DC power. So you're going to be using a charge controller to regulate the current and voltage going into the batteries. You're going to program that charge controller with all your charge settings from our integration guides. One important thing to consider when you're DC coupling is shading, right? So if you've got a line of panels in series, and one of those panels, just one, is shaded, you're going to lose, it's going to kill the output of that whole series string. So you want to be careful not to have panels in series if any of them are going to be shaded. A parallel would be a better arrangement there. Another thing to consider is that you're meeting the maximum, you're underneath of the maximum open circuit voltage and short circuit current that is acceptable by your charge controller. And even considering, temperature drops can increase the open circuit voltage of your system. So be sure to factor that in. So what does a charge controller do? We get this question a lot. Why do I need a charge controller? A charge controller is going to regulate the DC voltage produced by your solar system as it goes into the battery bank. So it's going to charge the battery exactly as it wants to be treated, as long as you program it correctly. So you can really use any source with a charge controller. Just make sure to check with the manufacturer before you connect something like wind or hydro. There are two main types of charge controllers: MPPT, which stands for maximum power point tracking, and PWM, which is pulse width modulation. So first, I'll talk about MPPT and how that works. MPPT is constantly detecting the solar output voltage, and it's constantly jumping up and saying, okay, are you going to produce more power if you're at 0.1 volts higher? No, okay, back down. Are you going to produce more power if you're 0.1 volts lower? No, okay, back up. And it's always finding that perfect power production point. So it's constantly tracking this curve and moving around on the maximum power point, the current voltage curve that the panels are producing. And it's up to 99% efficient because of this. Now, if you're installing a new system today and it's over 1 kilowatt, maybe over 2 kilowatts, then there's basically no question you're going to be using an MPPT charge controller. Now, if you're using a really small system or an older one, then you might be on a PWM charge controller. PWM is less efficient in larger systems, but it still works great. It's a very simple, tried and true method. It's going to reduce the pulse width. So instead of really modifying the current being provided to the battery over time, it's just going to provide the same amount of current for shorter bursts, right? And that's going to end up the battery just seeing the average of those bursts, because the switch is just opening so fast that the battery can't even see how fast that switch is opening and closing. The battery basically just sees an average of the amount of time the switch is open. So in a DC coupled system, the layout is very simple. Everything that is coupled to the batteries is going to land on this DC bus right here that I've highlighted in red. So your charge controller is going to output PV power at, let's say a 48 volt system. It's going to output 56 volts. The inverter is going to take that voltage right there and use it right away if there's a load on. If not, that power is going to be diverted into the battery bank for use later. So this DC bus is, it allows power to simply bypass the batteries. I know when inverters kind of were being developed a few years ago, maybe 5-10 years ago, there was a thing called a battery bypass feature, which really is kind of a gimmick because a bus bar acts as a battery bypass. But this is a really nice illustration because it shows you the general layout of where everything connects in a DC coupled system. It's obviously simplified a bit. Awesome. So let's touch on AC coupling as well. And then after that, we'll get into examples of what products to use in what applications and when you might want to go AC versus DC coupled. So AC coupling means that the power coming off your roof is immediately converted to AC. So your solar panels produce DC power, and there's either a microinverter on your roof or a string inverter right on the side of the house, converting that power to AC right away before it reaches any other components. So this was, very popular because it was a bit cheaper and easier to install for electricians trying to make PV systems that simply combated electrical bills, and they just sold power right to the grid as soon as it was produced. There's a ton of these out there. They're kind of, I'd say, phasing out. They're becoming less popular in terms of new systems. Most new systems, I don't see a reason to do AC coupled. Many of them are DC coupled in residential circumstances. It often makes sense to do DC coupled. So either way, whether you're AC or DC coupled, all of your loads are going to be powered directly through an inverter. So regardless of your system layout, you always need a battery-based inverter. So in this case, you've got the PV array, AC coupled inverter, and then your battery-based inverter and your batteries. So there's always the battery-based inverter, which is tending to your batteries. So in this case, the battery-based inverter we've shown here is a Solarc. Solarc's got a built-in charge controller, but also the inverter's charger acts a lot like a charge controller as well. So it can take AC power and convert it to the exact voltage the batteries want and store it for later use. So using a generator is also basically the same as AC coupling. The layout is extremely similar. An important thing to consider if you're adding batteries to an existing AC coupled system is frequency shifting. So if you haven't heard of this before, frequency shifting is how a battery-based inverter regulates charging a battery. So you've got this AC coupled PV array, it's producing power and sending it to your battery-based inverter. Now, if you're disconnected from the grid, you don't have anywhere to send that excess PV, and your batteries are getting full, and your PV is still producing a whole bunch of power, you have to basically tell it to, curb that, like produce less power or even no power. So the way your battery-based inverter does that is it mimics the grid, so it generates 60 hertz, and then as the batteries are full and it wants to curb PV production, it will increase that frequency to 60.1 or 60.2 hertz. The PV inverters will see that and reduce power output more and more as the frequency increases more and more until they eventually just shut off. So one thing to consider though is if your battery-based inverter and your PV inverters are compatible. So if you've got a super old PV inverter and a brand new battery-based inverter, the PV inverters might not have this feature and they might just shut off when the frequency shifting is trying to occur. So you've got to make sure you call, both your battery-based inverter and your AC coupled PV inverter manufacturers, give them a call and make sure that they're compatible. Basically, if you're working with the newest equipment on both ends, it's pretty much always going to be compatible. But again, if it's a bit older, you should definitely double check. So here's an example diagram of an existing simply AC coupled solar array with no storage, no battery-based inverter. You've just got your panels, microinverters, sub-panel, and main panel. Now, if you want to add batteries, you simply toss them in the middle. So it's between the critical loads panel and the main panel is where your battery-based inverter would come in. Another great fit here is our access units. Our access unit is batteries and inverter all in one, outdoor and enclosed. It's great because this equipment here, the AC coupled PV array, sub panel, and main panel, it's usually always outside. So having to, put an inverter indoors sometimes complicates the install. And when you've got an access cabinet like the one over here in my garage, it's a much simpler install. It's outdoor rated already. So we'll talk a little bit more about our access cabinets as we go on. But first, applications. So let's talk about when you want to AC couple and when you want to DC couple. First, DC coupling. If you're off grid and you don't have a massive system, you are always going to be DC coupling. It really makes very little sense to AC couple off grid unless your system is just unfathomably large, right? So DC coupling is going to be more efficient, and really there's no AC source to send your power, your excess PV to. So you're not selling any power. Why would you convert it to AC before putting it in the batteries? Additionally, any new systems being installed residentially, as I mentioned, brand new PV systems, when you come to DC coupled, you get a lot more benefits, a lot more features out of that. So we're talking about grid selling, time of use, and peak load shaving are a lot more controlled on a DC coupled system. The reason for that is on an AC coupled system, your PV, AC output and grid cell input are on the same bus. So it's really hard to separate those two and know if you're using your own power or the grid power. They're on the same bus, so it's really difficult to figure out where your power is coming from and actually separate them without just disconnecting one or the other. Again, when it comes to AC coupling, a lot of the uses here are just when you have the existing AC coupled array and you want to add batteries. You're not gonna find a lot of installers rewiring the whole PV array. It's probably cheaper to just add a battery-based inverter to take care of that and take the small efficiency loss. Additionally, if your main goal is, really only selling to grid, that's probably what you already have installed is an AC coupled array. So one thing to keep in mind here is if you're AC coupling and using existing PV, adding a battery-based inverter, you've got to make sure your inverter is Rule 21 compliant. So you can't just get some random eBay inverter from God knows where and just throw it on your system. You have to have a inverter that's going to make sure not to try to send power to the grid to sell when the grid is down, right? That'd be dangerous. You'd be hurting utility workers potentially, doing all sorts of messy work there. So you really need to make sure your system is capable of islanding, which means basically just acting independently from the grid. And it has to do that automatically. So that transfer needs to happen without you pressing any buttons. Large scale commercial and industrial systems sometimes are AC coupling due to the ease of installation, possible efficiency gains depending on what type of equipment and size. However, as I mentioned, be careful if you're seeking to really do some intense time of use arbitrage, peak load shaving, or self-consumption. The AC bus is the AC bus, and it's hard to separate where your power is coming from and where it's going. If you want to avoid using power from the grid, buying power during the most expensive hours, let's say 5 to 9 p.m., the best way to do that in an AC coupled scenario is just to disconnect from the grid from 5 to 9 p.m. But then you can't sell power to the grid from 5 to 9 p.m. So it's a tricky situation to combat there. And it's forcing manufacturers to get more and more creative. Rapid shutdown, one of everyone's favorite topic to argue about nowadays. When it comes to a DC coupled system, I find this is, pretty much the same. DC versus AC coupled, not a huge difference as far as the rapid shutdown requirements. If you've got a ground-mounted PV array, you can probably just use a shutoff box. And we'll show some examples of this as well, but some diagrams. But to talk through it first, if you're installing a brand new roof-mounted PV system, you're pretty much always going to need some sort of attachment on each module, each PV module. So that's either a DC optimizer with rapid shutdown feature or a rapid shutdown only attachment. Those are sold by Tigo. You can potentially use a remote trip breaker on a full string of PV panels. Though I see this is less common, the midnight birdhouse style. But the most common increasingly is the single button shutdown on the Solarc. So just the press of one button will disconnect the batteries, it will disconnect the inverter, it will disconnect the PV array all in one button and just turn everything off. As far as AC coupled, really it's the microinverters are doing what the DC optimizer are doing. Excuse me, the microinverters are doing the same as the DC optimizers, but they're doing it on the AC side. So an AC coupled array, your microinverter or string inverter is going to handle the rapid shutdown compliance. You're still probably going to have a shut off box or a PV disconnect. And you have the option of using that single button shutdown on the Solarc still. So let's jump into some diagrams for this. So this is a DC coupled example. Not necessarily that you need this shutoff box here, but I find that basically everyone either is required to install it or just does for convenience. However, you can also use a Tigo transmitter, and often people are using both. So a Tigo transmitter gets 12-volt power from the Solarc inverter, and if you press this red button, the rapid shutdown button, or if you just turn off the inverter, that 12-volt signal is going to disappear, and this transmitter here, when it's not online, these rapid shutdown modules or optimizers will just turn off immediately. So that kills PV production with the touch of a button, and it also would disconnect the batteries from the inverter and then cause the inverter to just shut off. So you can also use this single red button with an AC coupled system, but I wanted to give a different example of what is commonly seen. I see a lot of people using the XW Pro for AC coupling. They'll have a critical loads panel, and between their panels, their PV panels and their critical loads panel, they've got a rapid shutdown, just a shut off box here. As far as system design considerations, in a DC coupled example, you're going to be limiting the amperage through the charge controller, as opposed to AC coupled, which limits battery amperage through the inverter charger. When your PV array is down on an AC coupled system, all of your when your grid connection is down on an AC coupled system, that sends all of the PV power to the batteries. So in that case, you really need to be sure that your batteries can handle the amount of charge current coming from the PV array. So sizing is really crucial there. Whereas on a DC coupled system, I see tons of people having massive oversized arrays because of poor sun conditions or shading. And instead, they'll just limit the charge current very effectively through the charge controller. So simple programming done in 5 minutes will take care of that. A concern, though, with DC coupling is wiring runs. So if you have a very long wire run with a lot of current going through it, you're going to have a big voltage drop. And with that comes efficiency losses. On the other hand, AC coupling just doesn't have that issue. When you're looking at 120, 240 volts, it doesn't, there's really very little voltage drop across wires. DC coupling has more, smooth grid down transitioning. So as the grid, turns off, as your grid drops out, your system won't even notice. Your batteries and charge controller are really on one side of the system, and the grid is entirely on the other side of the system. They don't even notice if each other are present or not. Whereas with an AC coupled system, time of use features, like I said, it's going to be a little limited there. And self-consumption, selling, it's just not as ideal for those features, but it's often, a little bit easier for installers to figure out how to go about installing an AC coupled system. It may be a bit cheaper, and there's less strings and less wiring to worry about. Let's touch on which of our products is the most applicable in each scenario. So really the PHI battery, it's a battery. It's AC or DC coupled. It doesn't make a difference. The battery is going to see DC power. The battery is not going to see AC power. So it doesn't care whether you're AC or DC coupling, as long as you have a battery-based inverter to tend to it. If you're frequency shifting, make sure you're using a 48-volt system. This is really needed for the frequency shifting to work effectively. 24 volts would not be recommended for a system that's selling to the grid and frequency shifting. If you're using our AmpliPHI batteries, note that these are only compatible with SolarArc inverters at the moment, as well as Sunny Island. So these really are going to give you a more accurate reading as far as state of charge, more ability to monitor them, kind of like a fuel gauge. It's going to also talk to the inverter and tell it how much power it can handle. These are going to be better for, I'd say better for an outdoor installation, especially because they've got more intense BMS protections built in as far as low temperature or charging too quickly. But again, it's a battery, so it doesn't really care if you're AC or DC coupling, as long as you're using a compatible and communicating inverter like the SolarArc or Sunny Island. Now, our access systems are, I see, becoming very popular for AC and DC coupling. These are important because installers are getting permits much easier when systems are going outside the home. So in that case, you really need an outdoor rated enclosure. Sometimes the inverter can be inside of this enclosure. For example, we've got a Schneider access and a SolarArc access, both have a built-in inverter, and you can even add on a charge controller to the Schneider access as well. So really you can AC or DC couple with either of these options. I see them usually more used for AC coupling because all the equipment is already outside. The SolarArc is going to have an automatic transfer and UPS. So actually the SolarArc and Schneider access both have an automatic transfer and UPS. So they're going to switch over from running off the grid to running off battery power in a matter of milliseconds. None of your loads are even going to notice, and you're not going to realize that there was ever a power outage. So this makes them the top of the line for AC coupling. And again, easier for permitting because they have the 9540 listing, 9540A test report, and they're outdoor rated. So this is really perfect for throwing outside on an installation. Note that, battery temperature is not necessarily maintained by this. So this is a metal cabinet. So if your environment is going to get below 32 degrees Fahrenheit, I would highly suggest you use AmpliPHI batteries. AmpliPHI batteries are going to stop the inverter from charging them if they get too cold. They're going to tell that inverter, hey, I'm cold, I don't want that much current. And if the inverter doesn't listen, they're going to shut off. So they're really going to protect themselves in cold weather. If you're using standard PHI batteries that don't have that protection built in, you're going to want to make sure that you keep them heated or disconnect them as the temperatures get very cold so they don't charge below freezing. Now note there are some PV limitations to these access units. So the Schneider Access 3 battery can only have 5.7 kW of PV. The 4 battery version can have 6.8 kW of PV, and the SolarArc Access, you can couple 7.6 kW of PV. So these are important limitations. As I mentioned, remember, when the grid goes down, all of your PV power is going into the battery bank, and you need to make sure your batteries can handle that. Note that we've got tons of design tools. We're here to help you. Our calculators and sizing tools on our website can help you get an idea of the size of the system your customer needs. And if those just aren't doing it for you, give us a call. We're here. You can reach us by phone at 805-640-6700, extension 1 for technical support on existing systems and 2 for sales and pre-sale design. If you're installing our products already, make sure you sign up to become an Elite IQ installer. So this is going to help you grow your business for free. We're going to make sure you're getting a lot of exposure to customers looking to get SimpliPhi batteries installed. If you've got 2 installs, shoot me over some photos. I have my email on the next slide. We are going to get you into our newsletter. It's a monthly newsletter that goes out to a giant email list of customers, as well as a spot on our map. So when people are looking to purchase our batteries, they go right to our where to buy map, and that shows them where their nearest distributor or installer is located. Right there, your contact info will be, available on one of these flags here. And this really just going to help drive a continuous flow of business toward our repeat installers. So you can apply here. You can also just contact me for more information. My email is on this screen here. So email me at training@simpliphipower.com and I'll get back to you regarding our IQ program. If you need, recording of this video, it's going to be automatically sent to you. So don't bother, bugging me for that. No problem. You'll get one automatically. If you need NABCEP credits, this is the email to contact, training@SimpliPhi Power. And I'm going to jump into our Q&A. Are there solutions available to maintain proper battery temperature in outside conditions, cold or hot climates? I want to avoid shutdown in cold conditions. Yes, great question. There are tons of ways you can insulate your cabinet. If you've got a custom cabinet, it's probably a little easier to insulate. However, the Access and Boss cabinets do have a bit of room built in for you to add some insulation. Probably about 1 inch of foam on each side would be great. And you can put little heating pads that run off the inverter underneath of all the batteries. It's going to keep them nice and warm, and it's not going to use too much power either. So I think if you want more info on, heating pads we can recommend, just email me. That is a good way to kind of keep your system running in the cold climates and not have to worry about charging below freezing. Do you know if the Solar or Schneider inverters can accept a V2H input? Not sure what V2H is. They can accept a smart load output on the generator breaker. They can accept the grid on a generator breaker and vice versa. They're very flexible, but I'm not familiar with V2H. Does the Solar communicate with Phi batteries? No. So the Solar communicates only with AmpliPHI batteries. Standard PHI batteries do not have communications. They're a simpler battery, simpler BMS. It works similar to a lead acid battery. So you're going to, program the inverter and it's going to treat the battery as you've programmed it. Whereas the AmpliPHI have a bit more protection built into that BMS, a bit more intelligence and a brain, so to speak. Awesome. That is all the questions I'm seeing today. Thank you, everybody, for joining in, and I will see you all next time.